Okay, everybody. So we're going to go through the heat calcs with phase changes now, and we're going to utilize that idea, that delta heat of fusion of ice, which we just figured out. And we figured out that the heat of fusion of ice is 334 joules per gram. So what that means is that it takes 334 joules of energy to be able to melt 1 gram of ice. That's what that value means. It's similar to a specific heat value, except for there's no temperature component. So we use this delta heat of fusion when we're in a phase change with solid and liquid. So our new formula is going to be Q equals M times delta heat of fusion. Okay? And this value is, I'm just going to put parentheses around it so we know it's all one value. It's a constant value, just like a specific heat that we will give you if you need it. Okay? So we're going to go through an example of how do we use this to determine how much heat it takes to undergo a phase change. So let's say that we're going to have a piece of ice that starts out at negative 20 degrees Celsius. Okay? And so our problem is going to be how much energy is required to melt 90 grams of ice, which is at negative 20 degrees, to 75 degrees of water. Okay, so that's kind of our problem, and when we approach a problem like this, it's going to be different than our other heat calc problems. So when you read the problem, you're going to have different strategies. In this case, when you read the problem, hopefully what we want you to recognize is that we're going from ice to water. That's a phase change. And when I have a phase change, I like to reference and draw a phase change diagram. You're going to end up having to do this in 3 different parts. Okay, so the first part is, on our phase change diagram, we're starting at negative 20 and going up to 0. So we're first going to find the heat that's required when it's a solid. So I'm writing Q of S, and we are in going from negative 20 to 0, so there is a phase change. So we're going to use our MC and then our delta T formula. One little thing that's a little bit different is that the specific heat of ice is different than it is for water. So the specific heat of ice is different, which I'll let you know. Definitely. Okay. So the mass of the ice is, from our problem here, so we have Q equals the mass, which was 90 grams. The specific heat of ice is 2.03 joules per gram degree Celsius. And the change in temperature here is this tends to throw people off a little bit. The change in temperature is from negative 20 up to 0, because we're only dealing with this section of our phase change diagram. So if we're starting from 20 and going to 0, your initial temperature is negative 20 and your final temperature is 0. So T final was 0 minus the initial temperature, which was negative 20. So in our delta T, we're taking minus a negative 20, which is making this value positive. So when we take 90 times 2.03 times 20, what we get is 3654 joules. Okay. So it's taken 3,654 joules of energy to raise the temperature of our ice from negative 20 up here. So in the first step number 1, we calculated the Q of S, the heat of the solid there. So now what we've done, we've raised the temperature of our ice up to the melting point of 0. And now what I want to know is how much heat does it take to go from 0 degrees of ice, melting all of that ice into water. So we're doing our Q of our solid plus our liquid here. So now that we're in that phase change, we need to use our new heat formula. Okay? So our new heat formula is going to be Q equals M times the delta heat of fusion of ice. Okay? And again, this value here is just a constant value, which is the one we calculated in our lab. So Q equals our mass is 90. We're going to assume no loss of mass. And then 334 joules per gram. And when we multiply that out, we get 29,970 joules. So what we've said is that it takes 29,970 joules to be able to melt all of that ice and turn it into water. Now, graphically, I'm going to move it down here a second. Graphically, we are right here. Okay, we are graphically right here. We've taken all the ice and we melted it into water, and now we're going to go up to 75 degrees. We'll call that 75 degrees. So now we're going to find out how much energy it takes to raise the temperature of 0 degree water up to 75 there. So it's the Q of the L, the heat of the liquid there. And since we have a temperature change, we can use our old formula, Q equals MC delta T. So I've got Q of the liquid, and I'm going to go MC delta T. This is the specific heat of water, since we're in the water phase, or the liquid phase, I should say. So Q equals our mass, again, which is 90. Our specific heat of water, 4.18 joules per gram degree Celsius. And our change in temperature is T final minus T initial. Now, remember how we're doing this in sections. So the final temperature is going to be 75 degrees. That's where we were on our graph. I'll show you that in a second. And the initial temperature is the temperature where that section started, which was 0. When we calculate that out, we get 61,000, no, I'm sorry, we get 28,215 joules. Okay, 28,215 joules. Now, if I want to know how much heat it took to go from negative 20 all the way up to 75 degrees, what we want to do, maybe I'll ask you guys, how do we want to do that? We're going to add them all up. Excellent. We're going to add them all up. It's sort of like if in Google Maps it says, go from here to Woodfield Mall, drive a half a mile on Barker, drive 4 miles on Golf, and then maybe 2 miles on Meacham. The total distance, you're going to add up those values. So the total distance that we had was going from negative 20 to 0, melting, and then coming up here. So we're going to add all three of those values together to come up with how much heat total it took. So it was 3,654 joules plus 29,970 joules and 28,215 joules. Okay, we get 61,839, which I would probably round at this point to 61,800 joules, maybe with 3 significant figures from the original problem.